Today's video is going to be about graphing exponential functions. Before we begin, exponential functions are typically used to talk about population growth or decay. So population growth is going to be, if we have this graph, population grows exponentially. So it looks like this. It increases at an increasing rate. And then exponential decay is a different thing, and that is where it decreases at an exponential rate. And this here is going to be more like half-lives, which you may have heard about in science class. A half-life is the time that it takes a population to cut in half. And so that's what this graph is going to represent most of the time. And then this graph is representing population growth. So that's just a very, very broad idea of what exponential functions even are and how they apply to anything in real life. So the exponential parent function, and remember that the parent function is just the absolute most basic form of a function. This is f of x equals b to the x power. Now, this b can be any number, and it's still considered a parent function. Usually, we will see it represented with the number 2 because that's the smallest whole number that actually shows some shape on the graph. If you have 0 to some power, it's always going to be 0. And then 1 to any power is always 1. So the first number that actually shows a shape on the graph is 2. 2 to some power is going to change. And that lets you actually see the characteristics of a graph. So if b is greater than 1, then the function is an exponential growth and is increasing. So that's the shape I was showing you earlier. That kind of starts out small and goes up. If b is less than 1, it is called exponential decay. And it is decreasing. So that's the other way, where it starts really high and gets really low. Then an asymptote is a line which the graph gets close to, but never touches. So what this means is I want you to think about half-lives. So if I have a population and it gets cut in half, then that's going to be, a smaller number. And then that gets cut in half again. That's a smaller number. Well, half of a really tiny number out here is just a tinier number. It's never, ever, ever mathematically going to equal 0. Now, if you had a real live population, you're talking about this in science class with organisms and stuff, then when you get down to half of an organism, that's going to count as 0 in, a real life situation. But mathematically, every time we split that number in half, it's just going to be a smaller number. It's never, ever, ever, ever going to be 0. And so we have this asymptote, this line where y equals 0, or where our population equals 0, that our graph is never going to actually touch. It's going to get infinitely close, but it is not going to touch that line, and that line is our asymptote. So this entire first worksheet that we're doing is only parent functions. So everything on this worksheet is a parent function. So a lot of the characteristics are going to stay the same. And on this worksheet with parent functions, we are going to consistently graph the x values from -2 to +2. Because that's where the curve of our graph is, and it's going to show us the general shape of our graph. We're at least going to graph these points. We may graph more. But we're going to use our calculator to do this. So on your calculator, you're going to go to y equals, and you're going to type in 2 to the x power. And then we're going to hit graph. And so this is a parent function. If we were to zoom in, you don't have to do this on your own, but just to kind of show you, over here where it looks like we are touching the x-axis if you zoom in there, you're going to see that it's actually slightly above the x-axis. And if we zoomed in even more as we go further to the left, you're going to continue to see the same thing where it's very, very, very close to the x-axis. And see, your calculator even says that y equals 0 here. That is not true. It's just such a small number that your calculator doesn't have the space to round it anymore, and it's rounding it to 0 because it's out of space to put, 0.000000001. Okay, so this is never actually going to touch the x-axis. It's just going to get infinitely close. So that being said, we're going to go to, let me fix my zoom back. We are going to go to the table. So you hit second graph to get to the table. And we are going to graph starting at -2. And you'll see that before that, those numbers get really, really tiny. So -2 and, sorry, lost my train of thought. Okay, so I'm going to graph actually this whole section of the table because this 8 still fits on my graph. So I might as well graph every point that I can so that it's the most accurate. So back over on your graph, you're going to go to -2 and then up 1/4, -1, 1/2, 0, 1, and then 2, over 1 up 2, then 2, 4, and finally 3, 8. So those are all the points that fit on our graph that aren't, teeny tiny down here. So the way that we're going to draw this, because we know that our asymptote is at 0, is that we are going to get as close to that line as we can, try not to cross it, and then we're going to go up. Wow, that was bad. All right, so this is our graph. Now we're going to answer all of these questions. And this is the part that I was telling you is going to stay very, very close to the same for this entire worksheet because these are all different versions of the parent function. So the domain of a graph is the x values that you can use. So mathematically, we look at this and we say, is there any value I could put in for x that wouldn't work, that wouldn't give me an answer? And no, there's not. If this were a fraction, we would know that the bottom couldn't equal 0. If it had a square root, we would know that you can't take a square root of a negative, etc. But for an exponent, there's really no rule that says we can't put something in for an exponent. So mathematically, I don't think there's any restriction on our domain. But then we can look at the graph itself. And on the left side, we have an arrow, and it points to the left. So that means that our x values will go all the way to -infinity. And then as we travel along our graph, there's no disruption. There's nothing to say we can't use any of these numbers. And then here we have an arrow that points slightly to the right. Yes, it's going to take a very, very long time to get to, x equals 100 way over here, but it will get there eventually. So there is no x value we can't use. So our domain is going to be all real numbers. And you're going to see that it will be all real numbers for every single exponential function that we do. That is just a characteristic of exponential functions. Okay, our range is our y values. So our y values will definitely go up to positive infinity. But when we look at the downside, when we look as we go down our graph, this arrow, while it is going slightly downward, will never, ever, 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 ever cross the x-axis. So our y value can never equal 0, and it will never go below 0 either. So our range is y is greater than 0. End behavior is exactly what it sounds like. What are the ends of our graphs doing, or of our graph doing? So this says as x approaches positive infinity. Positive infinity is on the right side of the x-axis. So we want to know on the right end of our graph, is our arrow going up toward positive infinity, down toward negative infinity, or is it approaching a specific number or a limit? And in this case, it is going up toward positive infinity. On the left, we want to know, is our arrow going up toward positive infinity, down toward negative infinity, or is it approaching a number where it has a limit? And in this case, it is approaching a limit of 0. It will never cross 0, so it approaches 0. Our y-intercept is the place where x equals 0 and is always written as a coordinate. So at x equals 0, we have this point here at positive 1. So our y-intercept is at 0, 1. The asymptote is always the equation of a line, and in this case it is y equals 0. If I were to draw that line on our graph, that is the x-axis, and that is the line that our graph will never ever touch. It's also always going to correlate with your range. Your asymptote and your range should always have the same number, and it will also be one of the numbers in your end behavior. It could be either one, and you'll look at that in a minute. Okay, so on number 3, this is an exponential decay because the b value is less than 1. So it's going to look like it's reflected across the y-axis because it's going to be decreasing. So if you go to your calculator and type in the function 1/2 to the x power, make sure you put parentheses around the 1/2. We're going to graph all the points that fit on our graph. So I'm going to go to -3, +8. -2, +4, and like I said, you can find all of these in the table on your calculator. -1, +2, sorry, 0, 1, 1, 1/2, and 2, 1/4, and then the numbers get really tiny, so I'm just going to stop there. Then we're going to draw our curve in. Okay, so this is our graph for 1/2 to the x power. Our domain, once again, is all real numbers. On the left side, we have an arrow pointing left, and on the right side, we have an arrow pointing right. There are no disruptions in the middle to tell us that we can't use any of these x values. Our range, once again, is going to be y is greater than 0 because there is this asymptote at y equals 0 that our graph will never cross, and all of our y values are above that asymptote, so it is greater than. On the left side of our graph, our arrow points up toward positive. Oops, I'm so sorry. This is positive infinity. This is the right side of our graph. On the right side of our graph, our arrow goes toward 0 and will never cross it. Then on the left side of our graph, our arrow goes up towards positive infinity. Our y-intercept, once again, is at 0, 1. And our asymptote always coincides with our range and is at y equals 0. So you'll notice that this is almost exactly the same for every problem on this paper because these are all parent functions. In our next lesson about transformations, this will not be the case. Thank you guys for watching today, and I will talk to you again about transformations later.